Hello, everyone. Thank you for joining us today. Our project is the PLA Recycling Machine. And basically, the idea was to take all the leftover PLA from 3D printers, such as failed prints, supports, or just scraps. And we wanted to turn it back into a usable filament. PLA obviously being one of those wastes that adds up very quickly. So instead of throwing it away, we wanted a simple way to recycle it right here on campus. When designing this machine, our priorities were safety, reliability, and making sure that students could use it without needing a lot of help. The whole system includes a shredder, a pelletizer, an extruder, a cooling pathway, and a spooler. All of these steps work together so that the old PLA goes in and the new filament comes out. Here we have our work breakdown structure. Vu, our electrical engineer, handled all the electronics. He wired the motors, the heaters, the temperature controls, and programmed the Arduino so that everything runs smoothly. David, one of our mechanical engineers, focused on the shredder. He modeled it in SolidWorks, helped create parts, and make sure that the design was safe and easy for all students to use. Um, Jesus, another mechanical engineer, also worked on the shredder, but he mainly dedicated his time to the spooler. He designed the system that winds the recycling filament into a clean roll. And of course, the rest of us worked on the later parts of the machine. Alexis designed a lot of the pelletizer and cooling system. He also 3D printed prototypes and put together the cooling walkway that keeps the filament consistent as it comes out of the extruder. I myself helped with the hopper and extrusion system. I helped assemble parts. I also worked on machining and was involved in the testing and troubleshooting, especially when it came to cleaning the barrel. Alfredo, on the other hand, created the first extruder and pelletizer designs. He also helped fully design and assemble the cutter system, and he also worked with us during testing to make any adjustments. Uh, this slide shows the full recycling process. Obviously, the first step is the PLA strap gets shredded into small pieces. That makes them easier to process. Next, we clean and dry the pieces so they don't bring any moisture into the extruder. After that, the shredded PLA gets pelletized, making pellets just help the material melt more evenly later on. And then obviously we move on to the extrusion. We found that at higher temperatures, it made it too runny, the plastic. And of course, finally, the filament goes through a cooling pathway and then onto the spooler, which winds into a fresh roll. And by the end, we basically turn the old prints into new prints that the makerspace can use again.
PLA or polyactic acid is the most widely used material in 3D printing today. It's biodegradable plastic made from cornstarch, which makes it far more environmentally friendly than petroleum-based plastics. One of the main reasons PLA is so popular is its low melting point, which makes it easy to print with an ideal for rapid prototyping. Because of these advantages, PLA is the dominant material we use here at Cal State LA's Makerspace. But with that heavy use comes significant amount of waste. Even successful prints generate leftover material, supports, wraps, brin, etc. And of course, failed prints contribute even more waste. All of this unused PLA gets thrown away, even though it is a material that can actually be recycled fairly effectively. If we can recover that waste and turn it back into usable filaments or pellets, we can save money, reduce the makerspace's material consumption, and support a more sustainable circular workflow for students. To design a recycling machine that actually works, we first needed to understand the material properties of PLA. One important mechanical characteristic is that its shear strength, which is about 8.8 KSI. For a safe design, we applied a factor of safety and increased the shear strength used in calculations to around 13 KSI. Understanding the thermal behavior of PLA was also important. While its melting temperature is roughly 188 degrees Celsius, we rounded up to 200 for our design assumptions to give ourselves a comfortable margin. These parameters influenced everything from the choice of motor power for the shredder to the heating elements for the spooler. We began our design process by creating a Gantt chart outlining our planned timeline for the shredder and spooler components. Our initial research, and early design stages stayed close to schedule, but later phases were delayed. The main cause of these delays were design adjustments. For example, one version of the spooner couldn't be printed in the 3D printers we have available in our makerspace, so we had to redesign it entirely. These setbacks were part of refining the design into something realistic and manufacturable within our resources. We also evaluated several shredded concepts. This decision chart shows how we compared the different designs. Reliability and cost were our biggest factors because we were working with a limited budget and needed a machine that would function consistently. Since we were designing everything from scratch, these priorities guided us towards the more practical solution. Ultimately, our focus was on creating a recycling system that is affordable, dependable, and tailored towards the need of our makerspace community.
Hello everyone, my name is David Martinez, and I will be walking you through our shredder design. Through our research, we ran into a design that made us believe it was possible to build one of our own. In 2012, David Hackens was in search of a way to recycle plastic as part of his studies at the Design Academy in Eindhoven, located in the Netherlands. Little did he know that at the time, it was the beginning of a global community of plastic recyclers. Today, they are an open source global community that exists solely to reduce plastic waste. How? By recycling it, and this of course includes PLA. The precious plastics community has created 3 different versions of their plastic shredder, along with other machines that they use to recycle plastic. Many of them are built to recycle more common plastics, such as plastic water bottles, milk containers, and other common plastics you might see around. While their design is available for us to use, we had to recreate it using English units so that we can find material that is commercially available for us to purchase and use. Here's our original shredder design, the good old days of when everything looked great on a screen. We designed this with the intent of having a single rotating shaft to keep our machine size limited. 3 different variations of rotating blades with the orientation changing after 3 were set in order to always have at least one blade face in contact with the material being cut, which is PLA in our case. In the first semester and in the summer, we finished our original design and began to order material to cut. We ordered an extra 10% of required material and found that the size and shape of the material we ordered would save us money. For example, if we ordered a square piece of stock compared to a 5-inch tall rectangular piece that is just longer but with the same amount of cutting area, we would save ourselves up to $100. After our initial design was done and our material was selected, we were able to use a static simulation in SOLIDWORKS to determine our max force of 800 pounds force, or 3,516 newtons per cutting face, before our material yields. Through our simulations, we also added circular cuts to each corner of our hexagon to reduce the stress where our blade meets our shaft. On the edge of where the cutting blade area meets the overall diameter region, we can see that we experience a maximum von Mises stress of 56,835 newtons, which is a little over 3 ksi away from our yield strength. But we are comfortable with this design. The actual cutting force will be 1,658 pounds force. Each blade will exert a force of 7,500 pounds force maximum, which means our actual factor of safety is about 4.5. With this, we will surely be able to cut and validate if we can possibly even recycle other plastic materials such as ABS, PETG, and TPU, which are other common 3D printing materials. One thing to note is that when 3D printing is done, there is what is called an infill parameter, which controls the density of your material. Most people who 3D print do not use 100% infill because it extends the time that your print will take and the quantity of material being used. After we validated that we had the right design and material was delivered, we began a cut. In the image above is the Maxium 1515 abrasive water jet inside our very own makerspace. We wanted to maximize our time and be able to machine our design on campus as much as we could. With scrap material that was available to test our cuts, we were able to identify what tolerances worked in real time. This was a great learning experience. This machine deserves its own time because on its face, to be able to get a 2D drawing from SOLIDWORKS sounds simple. But in order to really understand how to cut using this machine, We first had to understand how it works, what its limitations are, and then figure out how we can make things more efficient. For context, I've spent the last 10 years of my life in the architecture, engineering, and construction industry, also known as AEC, working in Building Information Modeling, also known as BIM. This was a huge advantage for myself. For example, to get my 3D model blades to a 2D drawing, I had to export the face of my blades. The problem is you can only do one at a time in SolidWorks. Once the face is extracted as 2D line work, it is converted into a DWG file, which is what I'm mostly familiar with. Given my work experience, there are watermarks after each 2D face export. So when you bring in a freshly exported file to the waterjet machine, the person cutting your material has to spend time cleaning and aligning your single object to a good cutting location, which can be time consuming. We have 12 blades, 4 walls, 14 spacers, 24 fixed blades against the wall. That's 54 pieces total to waterjet. Different material thicknesses and size. In order to be efficient, once our tolerances were configured, I went into AutoCAD myself to draw out the exact shape of our stock material we were cutting from and position the line work to fit within the constraints. This is what you see on the image on the left hand side. This sped up our cutting process. Instead of cutting each blade one at a time, we were able to cut 5 blades in one shot. The second challenge we faced is the power of the waterjet itself. Our material wasn't as heavy to leave it and set the machine to cut on its own at times. We had to stack weights on top of our stock to hold down the stock as it was being cut. This made it harder for us to fully use all of our material at times because the slightest move would affect the cut and our material. For our motor, we received a half horsepower single phase electric motor. It has a rated speed of 1725 RPM with a 66% efficiency. Although it is not ideal for application, it is what was available and we figured we could give it a shot and make it work. To do this, we chose a 50-to-1 gear reducer with the intent of increasing our torque to shred plastic. We could have gone with a bigger ratio gear reducer, but we figured this should be enough and keep our size down for our reducer to not take up more space than we already were. With this configuration, each blade would produce a tangential force of 150 pounds force at the tip of each blade, which is enough to shred PLA that aren't big solid chunks. One thing we ran into while cutting our material is that our axis of rotation is set based on the motor. Why is this important? The input axis of our rotation is set at one height from the bottom of the gear reducer. Once we connected the two, we realized that we had about a quarter inch of a height difference, as you can see in the image on the left hand side. With the help of Blake Cordis, we came up with the idea to get a 90-degree angle piece of steel to fix the gear reducer to and to hold down to our tabletop. Problem solved, right? Not yet. How do you water jet this piece of steel to get holes in the exact spot you want to? You really can't. With it being such a small piece of steel and not too heavy or regular of a shape, we found even more limitations to our water jet. What you see here is our final design. This is what we water jet and what we intended to put together for today. Unfortunately, we worked down to the final minute and had more machining left to do. Although we couldn't completely build our design as we intended, we learned so much along the way. We bled from how sharp the blades were, literally, sweat from machining, shed tears from countless nights in SolidWorks designing only to test cuts that didn't work. We learned how to design and fabricate. Very similar to designing for 3D printing, only we weren't extruding our material, but we were extracting from our material. We learned how to work with tolerances and gained a true understanding of machine limitations. Even when we ordered extra material, we realized it wasn't enough at times. We worked throughout the summer to try to get a head start, and even when we felt like we made progress, we ran into issues that made us feel like we took 2 steps backwards and went back to the drawing board. We solicited advice from not only our advisor, but from other professors, YouTube, and fellow classmates. I want to personally thank the Makerspace, specifically Gene and Brandon, for helping me even when they were off the clock, Blake Cordis, Dr. Gupta, and my fellow teammates for all the help.
Hello, my name is Alexis Rayos Villa, and I'm part of the engineering technology team. So right here, we'll first start off with our initial design concepts. These were very theoretical concepts that we started off with the beginning research that we had just made, the initial research. So first of all, this is our first design. Here we can see a feeder, a barrel, extruder screw, the motor, and the nozzle. The main issue with this one was that the nozzle placement it was just very unrealistic. All the different products that we looked at online just had this nozzle at this end over here in that continuous horizontal orientation instead of this vertical orientation. As for the second design, you can see that we fixed that. We placed this nozzle on that horizontal orientation, and then from there it go through these rollers, fans, and the cutter, all going through this horizontal pathway. But the big issue with this one here was that it wasn't compact. It was a very long system, and we wanted to make this a very tightly packed system so that it doesn't take up too much space. The second issue that we had with this design were the nozzle complications. Here, we were already attempting to optimize the nozzle while we still couldn't before we even started actually building it and testing it out. So we decided against this. We decided we're only gonna go with a single extruded hole here for extrusion instead of two. First, we had to make it work normally, and then we could possibly optimize it. Then after that, we had our third design, which we actually did work on and start making it, a physical make the physical parts for it. So here, once again, very similar to the last design, except that this time we wanted to put this elbow shaped piece to keep it compact, which was one of the issues from last time, and go from that horizontal orientation to that vertical orientation. From there, we go through the nozzle, once again, fans, rollers, and cutter. So the issues here were the manufacturability of this elbow shape. Um, and what I mean by that is this inside path here. It's a very we wanted to get a smooth path here so that it wouldn't disrupt the continuous smooth flow of the PLA material, right? So that was our main issue. To get that was it's very difficult to make and it's very time consuming. So that was one of the main issues with this design. The other main issue was the tight fitment complications. What I mean by that is that some of these walls we're going to have bearings on them on the side so that it can hold the two rollers as well as the cutter. Unfortunately, it was very time consuming. We would have to use a four jaw chuck on a lathe to achieve this, and we'd require a lot of training and practice to be able to achieve the tolerance that we were looking for. The next issue was the material issue. We actually overlooked the fact that we were making these rollers out of, 3D printed material, which is a plastic, which they would be made out of plastic, meaning that the material that's being extruded through here would stick to the rollers instead of being tensioned and pushed through. And the next one was that unfortunately, this cutter wasn't cutting properly. It was actually the material being extruded was actually sticking to the cutter as it was rotating. And we actually have an image of that later down in the next couple of slides. So then our final pelletizing and extruding design was this one here. Uh, we have a very similar design once again, except that we changed this side over here. Instead of having that elbow shape, we decided to make a different cutter. And what I mean by this is that we used a pair of scissors mixed with a motor, and we made a couple of 3D printed pieces to put it all together. We assembled it, and we basically made a motorized scissor that would cut very, very uniform sized pellets. We went with this approach because it has less components. It also eliminates the sticking to the cutter. It saves us time and cost by a lot, and we get more consistent and uniform pellets, which is what we are attempting to achieve here in order to minimize the variation in the diameter size of the filament that's being extruded prior to spooling. Lastly, we have our cooling walkway and our spooler. So, quick overview of this, we can see over here the cooling walkway. We 3D printed the body with inserts for the fans. Right here, we can see the walkway. We have the guides and hooks to guide this 3D printed filament. The 3D printer filament hooks would actually go here. It's not displayed in this image, but in our final version, we actually have hooks here to keep the material from going up. We also have our fans to cool the material as it's coming out. And then for our spooler parts, we obviously have an empty spool because we need an empty spool to fill it up. And then we have our drill. Our drill is used to rotate the spooler, to rotate the spool to fill it up with this filament. Next is the stand. We place the stand here and it is attached to the drill in order to prevent it from topping over when the spool is full with filament because it does get quite heavy. Next we have nuts, 3D printed cones, and threaded rod. That's all right here, and it goes on to the other side so that it keeps the whole structure together.
And this is the electrical system overview. And this slide shows the main electrical components that are integrated into our system. We use two stepper motors for the top pelletizer and the bottom extruder screw, and each controlled by a TM542T stepper driver. We also have one DC motor for the cutter mechanism, and all the motor controls handled by the Arduino, which generates the speed and direction signals for the drivers. And we also have one switching power supply, will give which will provide the power for all the above components. And for the heating elements, we use two Ph.D controllers paired with two solid state relays. To each of those will switch 3 mica band heaters. So this is why we have total 6 mica band heater, 3 for the top pelletizer and the other 3 for the bottom extruder. And based on the data sheet of the band heaters, these heaters require 220 volts. So we use a step up transformer to convert from the 110 volt wall outlet. And together, these components form the complete electrical system for driving the motors and maintaining stable temperature in the pelletizer. And here's the breakdown for the power calculations I used to select the correct power supply and transformer. So our stepper motors run on 36 volt DC, and each motor draws up to around 4 ampere based on the driver settings. And the DC motor for the cutter adds about 30 watts, and the Arduino and cooling fan adds another 15 watts. For the on the AC side, the heaters dominate the load. So we use total 6 mica band heaters, and each will have 150 watts, which adds up to 900 watts. And these heaters require 220 volts AC, so that's why we need a step-up transformer. So in total, the DC system requires roughly around 400 watts, which is why we selected a 550 watts, 36 volts, and 16.6 ampere switching power supply. And on the AC side, we would need a 1200 watts step-up transformer. And based on what we researched, we found that the PLA melting range is from 180 to 230 degrees Celsius. And to determine the optimal extrusion temperature, we performed multiple tests in this range. For each test, we recorded the filament quality, flow behavior, and stability. Across all the trials, we found that 180 degrees Celsius consistently produced the best filament. At this temperature, the PLA flows smoothly but still maintain enough viscosity to form a solid, uniform, and repeatable string. As the temperature increased towards 200 to 230 degrees Celsius, the material became more watery, causing the filament to thin out, lose shape, and become inconsistent. And here's how the control loop of how the system temperature works. So our temperature control system uses a closed loop design. The thermocouple measures the actual temperature of the heating barrel and sends that signal to the PAD controller. The PAD then compare the current temperature to the set temperature and calculate how much power is needed. After that, it will send a control signal to the solid state relay, which got a SSR. And that SSR will switch the 220-volt heater on and off accordingly. So for example, if we set the temperature to 180 degrees, the SSR will keep sending power to the band heaters until the PAD display the current temperature is close to the set temperature. And once it's reached to 180 degrees Celsius, the SSR will stop and the heater will stop heating. This loop keeps the temperature stable and prevents overheating, which is critical for consistent extrusion. And this is when we test the filament. So as you can see in the picture, on the left picture, we tested with 210 degrees Celsius, and the filament comes out to be watery and not consistent. But when we change it, but when we lower it to 180 degrees Celsius, the filament comes out as we desire. The thickness comes out of this barrel is 1.75 millimeter, which is perfectly. And this slide shows the complete power distribution layout for our system. So first we start with 110 volt AC from the wall, and this feeds into a 110 to 220 volt step-up transformer. Since the Mica band heaters require 220 volt for the best performance, so I plan to use the 220 volt AC for the whole system. So for the step-up converter, the AC power is split into two main branches, one for the heating system and one for the DC system by using terminal blocks. So as we can see on the left side, the AC goes into two PAD controllers, and each PAD controller drives a SSR, and each will turn on and off the band heaters. So this branch is responsible for maintaining a stable extrusion temperature. On the right side, AC power is fed into a switching power supply that converts it to 36 volts DC for the stepper motors. Because the motor's driving voltage is 36 volts DC, so I will use 36 volts to power the two stepper motors for individual drivers. It also feeds two step-down converters, one drops to 9 volts for the cooling fans and the Arduino, another drops to 12 volts for the cutter DC motor. All signals and motor control receive commands from the microcontroller, which coordinates the motion of both motors and the cutter. Overall, this distribution design separates high-power AC components from low-voltage DC electronics, ensuring both safety and stable operation across the entire system. And this is the flowchart for embedded system. This flowchart shows how our microcontroller operates. So when the system powers on, the cooling fans automatically turn on for safety, and the controller then waits for the user input. So when we press the button number 1, that will start the motor. That will start the first motor, which is the motor on the top for the pelletizer, and pressing button 2 for the motor number 2, which is the extruder system. This simple logic lets us independently control each motor while keeping the system easy to test and operate.
Okay, so moving on to the final assembly, we will start with the first step where shredded PLA is fed into the hopper connected to the first extruder, where a lead screw pushes the material through the barrel of the extruder, melting the PLA through the use of 3 band heaters, working at 185 degrees Celsius. As the PLA melts, the extruder applies pressure to push the filament out and onto our next step. Our pelletizer consists of fans to cool the heated PLA as it comes down, as well as a cutting system in the form of motorized scissors, which we installed using a DC motor, and finally, a mount to keep the scissors centered to where the filament will land in order to be cut. Here's a visual of our pelletizer assembled onto the machine. We set up the fans at different heights to keep the cooling consistent, as the extruded filament travels down to the cutter, which is placed at the bottom. From there, the new pellets will fall onto the next hopper in order to be extruded as a finer type of filament. The whole purpose for the second extrusion process is to create uniform clean pellets, which allows for the final filament to be more uniform, therefore creating less defects during printing. All of these pieces come together to make our full assembly, which consists of both the first extruder at the top and the second extruder at the bottom, both with mounted band heaters to heat the PLA as well as hoppers to ensure the shredded and pelletized PLA fall into the extruders. There is also the pelletizer in between, working as a bridge to connect the two extruders with a mount for both the fans and the cutter to begin the pelletizing process. Finally, for our results, the extruders worked well to create new filament from shredded material. However, we had many occasions where the barrel would clog, which required proper maintenance to continue testing, as we found that without cleaning the extruder properly, our testing led to very burnt filament, which would also melt and kind of combine with new filament. That would later result in a mix of either different colored or burnt filaments. Even so, with the proper care, the extruder achieved its goal and created filament at our desired diameter of 1.75 millimeters and with the correct color as the shredded material that was used. Our cutter, however, had many issues. Originally, we planned to cut the filament using a rotating two-blade router bit with a 1/4-inch shank to have more consistent cuts with a constant speed. But testing showed that the filament was sticking to it and rotating with the blade as opposed to being cut by it. In an attempt to resolve that issue, we were looking on changing the speed, but then later decided to completely switch directions as we wanted to have cleaner cuts using a horizontal cutting approach. To do so, we created our new motorized scissor cutter, which uses a crankshaft to open and close the blades to cut the filament as it comes down. However, it was not able to cut the material consistently enough to start the next extruding process, as you can see here, where the router bit was not able to cut the filament at all, and the scissors did cut the material, but it would either bend it or deform it and then cut it, creating long pieces that were not usable for the final part. And finally, for the spooler, in order to test it, we used other PLA pellets to test the second extrusion and found that it also worked in extruding filament, which we then extended out and onto our spooler, running the filament through the cooling walkway, which did work in spooling the final filament.